All right, good morning, everyone. Great to have you, whether you're in person today or online. My name is Jane Harrison with North Carolina Sea Grant. I'm going to be moderating this session on agriculture. And just so the speakers are aware, we have 20 minutes for each speaker. Please take 15 minutes or so for your presentation. And then we will have Q&A for a few minutes as well. And I will put up these little notices. So when there's 5 minutes left in that 15-minute time period, you'll know. If you go over, not a big deal. We'll just have a few less minutes for questions. I am going to introduce first Lise Montefiore, and she is with NC State University, and she will be giving a talk on reconstructing the historical growth of the swine industry in North Carolina. Lise. Mm-hmm.
Hello, so thank you very much for being here. So I will present you part of my research that was part of my dissertations, and that was funded by Sea Grant and the NC Water Resources Research Institutes through graduate student fellowships. So this project aims to reconstruct the historical growth of the swine industry in North Carolina. So for those who don't know, North Carolina is the top producer of hogs and pigs and ranks second nationally in the production of this animal species. So you can see here on this map, the red dots represent swine operations. And you can see in North Carolina, they are mainly clustered in the eastern part of the coastal plain of North Carolina. So in North Carolina, the swine operations are also known as swine concentrated animal feeding operations, and they are commonly composed of several metallic buildings in which the animals are contained, and from one or two open-air retention ponds, also called waste lagoons, in which the animal waste is discharged. So regularly, the liquid waste of the waste lagoons is spread into adjacent fields. They are known as spray fields, and the spray fields are grown in order to absorb the nutrients from the animal waste. So in North Carolina, we have over 2,000 swine operations that use this type of management practices. So now if we look at the swine industry growth over time in North Carolina, we observed a dramatic increase starting in the late 80s until the end of the 90s, with a plus 400% in hog inventory. Until 1997, the growth reached a plateau. So the plateau was mainly due to the place of a moratorium in 1997 that restricts the construction and the expansion of swine farms and requires lagoons to be permitted. So the moratorium was extended until 2007 when it was made permanent. So prior to 1997, the locations of swine CAFO were undocumented. So the data are only available at the county scale for the USDA Ag Census data. So we can know the number of pigs per counties. And this type of data are only released every 5 years. So we do not have spatially explicit information of the years of constructions of waste lagoon of swine CAFOs, but such information would improve our understanding of the long-term effects of the swine industry on water resources and surrounding communities. So the research objective of this project were to reconstruct the historical growth of swine CAFO prior to 1997 using satellite images, and to analyze trends in a waste lagoon construction in relation to water resources. So the first step was to choose satellites. So we have the Landsat program that encompasses now 9 satellites. So the Landsat program is the longest running enterprise for the acquisition of satellite imagery on Earth's surface. And this program started in 1972. So among all of the satellites available, we have the Landsat 5s, which collected images from 1994 to 2013. And this time period coincides with the exponential growth of swine farms in North Carolina. So this satellite was found adequate for the analysis. So here you can see several images of Landsat 5 in North Carolina for different time. So you can see on these images black dots that increase over time, and these black dots represent swine waste lagoons. So you can see on these images, the black dots are very visible and distinguishable from other features, notably. So we can really identify them due to their spectral properties. So the time series of Landsat 5 images and the spectral properties of the waste lagoons, we can identify the year of construction of the waste lagoons. So a little bit more information on the methodology. So here I'm just presenting you an example for one waste lagoons, and the method was applied for all of the waste lagoons, swine waste lagoons in North Carolina. So the first step was to retrieve waste lagoons locations, the coordinates using Google Earth. So Google Earth provides very high quality images in which we can really pin in the center of each swine waste lagoons and retrieve the coordinates. Then we can import the locations in Google Earth Engine. So Google Earth Engine is a cloud-based platform that allows planetary scale analysis. So we can have access to thousands of satellite images, and we can perform analysis without downloading any images on our home computer. So with Google Earth Engine, we were able to get access to all of the Landsat images from 1984 and 2012 in North Carolina. And we could get access to a high quality satellite images with a cloud cover inferior to 5%. So now with these images, we were able to extract the near infrared reflectance time series at the location of the waste lagoons and to get this time series. So you can see that at one dot represents one value of the near infrared reflectance value at the location of the waste lagoon. So for one images at one time. So that's how we can get the time series of the reflectance at the location of the waste lagoons. And on this time series, you can observe a dramatic decrease in the reflectance. And this decrease corresponds to the year when the waste lagoon was constructed. So when we checked satellite images before in the time series in 1996, we do not observe any waste lagoons. And right after the dramatic decrease in the reflectance, we observe the waste lagoons. So the reason why we have this decrease in the reflectance is simply due to the waste lagoon spectral properties, because a waste lagoon is composed of water, and water absorbs a lot the near infrared. So when a pixel transition from land like crops or forest to water features such as waste lagoons, the reflectance decrease. So we were able to determine the year of construction of the swine waste lagoons by automatizing the change point detections for all of the waste lagoons. So we have over 3,000 waste lagoons, so that represents 3,000 time series for which we detected an abrupt change in the time series between the two segments. And then we use of a validation data sets that represent 10% of the initial data with all the waste lagoons, for which the year of construction of the waste lagoons were known. So the results reveal that we were able to detect correctly over 95% of the waste lagoon construction year in North Carolina. So this number was based on the validation data set. And on the animations, you can see the growth over times. And notably that even before the period of records of the Landsat, we have already a lot of waste lagoons that were already clustered in the coastal plain of North Carolina. And later after, the clustering increased and expand a little bit outside the bounds. So this histogram shows you the number of waste lagoons built over times, and the dots, the cumulative number of waste lagoons. So the new data improves the resolution of available information. So before we had the data at the county scale, and the data were released only every 5 years. And now with the new data set, we are able to aggregate the data at different spatial scales. So for example, we can do it at the hydrologic scale UC12. And if we look, for example, at the Duplin counties, we can observe for the same area more variability in the number of waste lagoons. So this new data improves the quality. So we have higher quality data that will allow different spatial temporal aggregations. So different information and so different analyses will be permitted. So now when we look at the historical reconstruction of the swine CAFO growth since 1996 at the watershed scales, so we look at the lower PD, the Cape Fear and the Neuse watersheds. So in all of these watersheds, we observe the same pattern. So all these watersheds had already swine waste lagoons constructed before 1987, for which we cannot assess the year of construction because we did not have the satellite images available. And we observed a dramatic increase in the number of waste lagoons early in the first half of the 90s. So in 92, 93 until 95. And then we see the impact, the effect of the moratorium on the construction rate of the waste lagoons, represented by the red dots, where you can see a dramatic decrease in the number of waste lagoons constructed in North Carolina. So we observed that the moratorium didn't stop the construction of waste lagoons, but it seriously decreased the construction rates. Also, something interesting to observe, it is that just before the moratorium, we observed a decrease in the construction rate of waste lagoons prior to the moratorium. So even before, we observed a slight decrease in 1996, 1997. So now we also wanted to assess the spatial temporal distribution of swine waste lagoons in relation to water resources. So for that, we computed the distance between the nearest water features to swine waste lagoons. And we use the National Hydrography dataset, the NHD used by USGS. So the NHD is a dataset that will give us the shapes and the location of different water features, such as canal, lake, pond, reservoir, stream, river, or swamp marsh. And among all of these results that are presented here, we observed that 92% of the swine waste lagoons were less than 500 meters from the nearest waterways for all the time periods. And also we observed a slight increase of the distance over the times, confirmed by a Mann-Kendall test. So this might result either by a better understanding among the environmental and agricultural managers about the effects of the waste management practices on surface water quality, or either just because due to the swine growth, swine industry growth, the location was due to space constraints. So we don't really know, but we just can observe a slight increase over time. And finally, we observed that some energy water features were misclassified as waste lagoons. So we counted about 150 energy water features misclassified as waste lagoons. So the energy are often used in ecological studies, may not only serve as habitat assessment. So such misclassifications can induce some errors in the analysis of such studies. So to conclude, so the construction years of the waste lagoons were estimated with the 94% accuracy with a new methodology framework developed. So the new data, so the data are available online, increase the resolution of available information on the expansion of the swine production industry and improve our understanding of land use change in North Carolina. And documented trends could inform waste management practices at different spatial scales, so either the administrative scale or the hydrologic scale, for example. So thank you, and let me know if you have any questions.
Great. Thank you, Lisa. If anyone has questions, please, you do need to use the mic. I can also bring it around to you. I don't have any questions yet on the chat.
Thank you for that really nice talk. And I also greatly enjoyed your paper.
Thank you.
What next steps are you planning to do, if any, on this research, interesting research?
So right now, I would be interesting to assess with water quality trend, long-term water quality trends to see, based now that we have the construction years of West Lagons, if we could see an impact on the long-term water quality trends. And also something that would be interesting is to study the nutrients legacies, because we know that nutrients can accumulate over time in soils. So it will be interesting to run some modeling to quantify the nutrients legacies in North Carolina due to the swine industry.
Hey, thank you for your presentation. I have a question just about the NHD data set. So how did you distinguish between like the ponds and reservoirs and lakes?
So it is in the NHD, you have all the information. So it's shape files and they directly identify the water features as ponds or a reservoir.
Okay. Yeah, because maybe that's the difference between like NHD or NHD plus. But the ones that I was using, it just had like streams and ponds. So it didn't have like reservoirs or other waterways that you were showing. So I was just curious about maybe you had like a criteria for defining that or.
No, it's
okay.
really from the data sets.
Thank you.
I really keep that. Yeah.
Any other questions? Okay, Lisa, I just want to say thank you so much for this work.
Thank you.
Yeah, I think having that spatially explicit data set has a lot of possible future research options. So excited to see what you do next.
Thank you.
Yeah, thank you. And we're just going to wait until exactly 10:05 to start the next presentation. Okay, so our final speaker today in the agricultural session is Mahmoud Shehata. Nice to meet you. He is with NC State University, and he is going to be talking about spatial variability of soil thermal properties and moisture content using novel fiber-optic distributed temperature sensing techniques. All right, and I'll let you know when there's about 5 minutes left. Presentation.
Sorry, what?
I'll let you know when there's 5 minutes
Perfect,
left.
thank you.
Yep.
And you can use this for the back. And can I use the keyboard too? Yeah. Okay. Yeah. Okay. Perfect. Thank you for joining us today. So I am a postdoc in the Department of Biological and Agricultural Engineering here in the state, and today I would like, as she introduced, like to discuss with you like how to use the novel techniques of distributed temperature sensing to measure soil thermal properties and soil moisture and their variability across scales. So to start as an introduction, soil moisture variability depends on many factors, and which depend also on the scale, as can be seen from this figure from Benj et al. 2017. For many applications, we need to measure soil moisture over different spatial scales within the spatial scale spectrum. However, current techniques to measure soil moisture is limited only to point or micro scales and macro scales. And all these techniques have limited applicability when applied to the intermediate spatial scales ranging from meters to thousands of meters. So there is an opportunity to fill this gap by the new advances in distributed temperature sensing, which allowed us to measure the soil temperature along a fiber optic cable installed in the soil over several kilometers with a remarkably like high resolution of 12.5 centimeter and temporal resolution of 1 second. So some of the applications that can be used like to use distributed temperature sensing to measure soil moisture can be classified into like a single probe heat pulse system or dual probe heat pulse system. So in the single probe heat pulse, we apply a heat pulse into the heating element inside the fiber optic cable itself. And we measure the corresponding temperature variability. And from this, we can estimate soil thermal conductivity. And we are not able to measure the other thermal properties, basically. This thermal conductivity measurements can then be transferred to soil moisture if we know the relationship between the two parameters. However, the relationship depends on the soil type and also on the soil physical properties such as bulk density. So this is why the main limitation of such technique is to use how to characterize this relationship between lambda and soil moisture condition, and how to deal with its variation across long spaces, spatial scales. On the other hand, we have the dual probe heat pulse system, in which we apply the heat pulse at a heating element, which propagates through soil, and we measure the corresponding temperature variation at a distance. This setup allows us to measure all the thermal properties, including heat capacity, which fortunately have a linear relationship with soil moisture conditions. So basically, this technique doesn't need the soil-specific calibration required for a single probe heat pulse system. So the remaining of the presentation, I will give you like some of the results of the studies we performed to how to improve these two systems to get accurate and also easy to implement system to measure soil moisture conditions and thermal properties. I will start with the dual probe heat pulse system, and in this system, we first started to investigate it in laboratory setting. So basically what we did is that we installed a sand column, and we tried to address the two main problems of this system, which basically its dependency on this or its sensitivity to the spacing between the two probes, and also the adequacy of the soil of the distributed temperature sensing signals to its application. So to maintain the spacing between the probes, we proposed using a thin plastic mesh to maintain that spacing accurately. And we wanted to test this system, so we bought it in a sand column. So basically what you see here, if you take like cross section 1.1 here, you will see 7 fiber optic cables. 2 of them were heated, and the surrounding fibers were used as a temperature sensing. So we had like 4 sets of sensors across the whole sand column. And then we tried to take measurements at different soil moisture conditions. And we tried to analyze it. So basically, the signal or the temperature variation you get, so the temperature variation you get is basically like the figure in the top of the screen. So how we can estimate soil heat capacity, for example, from this signal? The traditional way to do that is just to use a simple model which rely on the maximum temperature variation and the time to attain it. However, this system can be problematic if you have a little noise in identification of this peak. So this is why, to make this system more suitable for the slight noise you can find in distributed temperature sensing, we propose a new approach, which basically using a more sophisticated model that account for the thermal properties of the fiber optic cable itself and fit it to the whole temperature variation signal. Then if you get like the heat capacity, using this simple equation, you can estimate the soil moisture conditions. And the information you need to do so is just like the bulk density and also like the composition of the soil itself. But even if you don't know this information, you still can estimate the changes in soil moisture because it has a correlation, direct correlation with the changes in heat capacity. So when we did this analysis, we found that, first of all, that the new proposed technique to process the data, which is based on the Knight et al. 2012 model, managed to give better accurate results all over the place. As you can see from these two figures, the first figure is comparison between the heat capacity estimated from the distributed temperature sensing on the x-axis against independent soil heat capacity sensors. And the bottom one is the estimation of soil moisture against also independent soil moisture sensors. And from the results, you can see that the Knight et al. Model maintained like very accurate results in contrary to the traditional method because basically of the noise in the signal. So based on these results, you can see that the optimized dual probe DTS system, and when I say the optimized, I mean using the mesh to constrain the spacing between the probes and also using an adequate data processing system, can estimate soil thermal properties and change in soil moisture conditions within 3%, which is comparable to any like commercial soil moisture sensors you can find in the market right now. And actually the key message here is that you don't need a soil specific calibration for that. We then this was like conducted in a laboratory setting, of course, very controlled, so controlled environment. So we wanted to see if still we get some accurate results under field conditions. So basically what we did is that we installed a 30-meter of this fiber optic cable in Lake Wheeler Center Pivot here, facility here in Raleigh. And we installed 18 soil moisture sensor along it. And then we took several measurements at different soil moisture conditions. And we wanted to see how the system performed. And basically also, instead of using only one sensor, we used different combinations. So basically the temptation behind that is to see if we can replace the heating fiber optic cable with just like an ordinary 20 gauge heating element. And actually the results, as you can see here in the results, we saw like that for most combinations, we were able to measure soil moisture conditions with a root mean square error of 2%. However, for one single combination, which we had like a new fiber optic cable we were testing, we found that it is not adequate for that application because of its structural composition itself. However, the main message from this experiment was again demonstrating the applicability of using the double probe heat pulse system in estimating soil moisture conditions. So now let's shift gear to the other system, which is the single probe, in which we apply the heat and measure the temperature at the same location using the same fiber. And again, the main advantage is that it is easier to install. However, as we discussed earlier, you can just use it to measure the thermal conductivity. Basically, if you get like the change in soil moisture, the slope of the relationship between the logarithm of time and the temperature variation, you can find that. So the key problem is that if you have like soil specific calibration, and if you have like variation of the soil across the scale, how you can assign this variability? If you have like different calibration curves, how you can still get accurate measurement using this system. So what we did is that we installed a 650 meters transect, and we installed also a lot of soil moisture sensors along it. And then we tried to see what is the best approach to calibrate this system. The figure here shows you the relationship between the thermal conductivity and the soil moisture on the y-axis. And you can see that there's quite a range of variability here. However, like the traditional way of calibrating these systems was just like to hit a single curve and assume it is universal and neglect all this variability, which, as you can see from here, can be problematic and lead to excessive errors at certain locations. So instead of that, what we proposed is to use a statistical learning approach, basically using the information embedded in the thermal conductivity profiles we have to better guide how we can calibrate the system. So we fitted a Gaussian processes regression model to the data, and the predictors we used is the distance of the point, the thermal conductivity measurements, And also we included the changes in soil thermal properties as the soil is draining from new saturation conditions, because this also will show you like the different soil properties, how they are acting from new saturation conditions while draining. Also, we included like the mean soil moisture and the temperature variation. So when we did the validation, you can see that the Gaussian processes model managed to give more accurate results in comparison with the traditional method, even for the stations where it was really different, such as station 11 and station 18. And it managed to reduce the root mean square error from like 5% to 2%, and the maximum error from 11% to 7%. And this is a figure just to show you like the type of high resolution data that you can get and the most information you can get from such application, as it's showing you like which places are drying faster than each other and etc. And this kind of information can drive like practical applications such as precision agriculture, etc. For the sake of time, I just like focus on a small like application of this is how to use this high resolution system to guide and improve remote sensing validation. So if you have like a remote sensing pixel, you normally have like some grounds like measurements to validate it. But how you can know that the ground like points are representative of that pixel? So what we did is that we took like small segments of this lens, and we, for each segment, we determined what is the number of samples required to accurately estimate the mean soil moisture and the standard deviation of soil moisture within this scale, within a certain accuracy, for example, 1%, 2%, 3%, and with a confidence of 95%. And the result here show you, like, for example, that for scales from like 5 to 350 meters, you need just like around 13 samples to estimate the soil moisture, mean soil moisture within that range with accuracy of 3%. And you need a lower number to estimate the standard deviation, basically around 6 or 7 samples. So all this data can give you like a sense how this can provide information for remote sensing validation. So just to conclude here, the systems, the DTS systems are improving, and they have like better potential now to estimate soil moisture accurately, and they have also applicability to be applied in the field. However, of course, still further research are required to increase that. And the application I give you here is just like the tip of the iceberg. So we are still like understanding how this unprecedented high resolution data set can support many applications. For that, thank you for your time, and I am happy to have any questions you have.
Great, thank you, Mahmoud. Are there any questions? I'm just checking the chat. I think we're pretty quiet there. Mahmoud, are there any other next steps that you see? In this,
we are basically like still also understanding the applications of that.
Mm-hmm.
For example, let me hop in out of here. I don't know how many minutes we still have.
We just a couple. Yeah.
Okay, so for example, let me.
You're still sharing.
How
are you trying to get back to your PowerPoint?
Yes.
Or the P down at the bottom?
I just wanted to start to present it.
Press that one.
I don't know where's the mouse.
Is that working? Oh, yeah, where is the mouse?
Let's see. Sorry, can you help us? Yeah.
The mouse has disappeared.
Yeah,
it's on the other screen.
Oh.
Okay.
Are you trying to start it?
Yeah, just open this slide. Yeah.
Okay.
Thanks.
Well, it should. Oh, now.
Okay, so this is also like another application we started to think about is how to improve like the downscaling of remote sensing products. So basically, we wanted to see how the observed variability is related to the spatial resolution of your measurements itself. So if you have like coarse measurement, you will see smaller variability. So how can you downscale that to inform like better application? So what we did also again is that we upscale the data and studied that. And what we found is that the standard deviation and the coefficient of variation decrease with the mean soil moisture conditions, which basically indicates that at new saturation conditions, we have less variability. But also what we can get from that is drive an equation to estimate the variability at certain scale if we have another data set with a different scale. So this have actually like great potential to improve like, and also to like integrate this with different remote sensing and aerial imagery techniques to support precision agriculture applications. And this is just like one application, but of course we are investigating others. Thank you.
Thank you so much, Mahmoud. All right, everyone, we are going to have a break now. So please take your time and then find your next session, which should start, let's see, at 11:15.